Today is my great pleasure to invite my colleague and my advisor, Professor Bernold Fiedler again. He has given 3 talks in this webinar, and today he's going to talk about his dissertation and the new application for recent publication about growth bifurcation to stationary solution and PI solution. And this is a very useful technique, and we are very curious about that. So welcome.
Well, thank you very much for the opportunity to speak here, of course. And I have to correct the introduction because Jayan Dai said my advisor, and it is not true. It is former advisor. And as always, when young people emerge and erupt into a flurry of publications and activities, is that they become your advisor. This is the most happy circumstances of our teaching profession. Also, I would like, it's a special honor to be invited to the seminar of our recent outstanding young scientist of NCTS awardee. And yes, and now this talk, it is not a continuation of a previous talk. It can be listened to independently, but it is a thread. Since Jayan invites me to his seminar, as it seems, on a regular basis, I have thought about a series of titles in advance. So this Roman 1, stationary and periodic solutions, can be seen as the start of mostly as a sequel of mostly independent things. I think I can easily go up to number 5 or so that I know what to do next just in case the occasion happens. So much for the thread. So today I want to talk about bifurcation from a genericity point of view. And what do I mean by genericity? By genericity, I mean a topological notion of many or most. You see, between Baer and Lebesgue, there was a big controversy in Paris. What is how to give meaning, mathematical meaning, to when something is happening most of the time. So generic, the English word of generic means something like typical, okay? A generic, how should I say? A generic introduction would be the speaker has done this and this and this and this and that, and then half of the time of the speaking time is already over. So genericity is one way to express that something is typical behavior. And an opposite a complementary notion is Lebesgue almost everywhere. So frequent in the sense of measure, full Lebesgue measure. And you see, there are generic sets which are topologically big. So Baer's notion is topological, and which are Lebesgue measure 0. And they are, and of course the other way around. Okay. So you can imagine how these guys had a very good time together, figuring out who was right. Now, so what is Baer's theorem? Let me start with Baer's theorem. And also another remark I should make is this is not a presentation of the style, I did this and this and this and that, and now you have no chance to understand it, okay? This is more of a lecture style. So I want to give an opportunity to the people who are not in the video now to learn about these techniques quickly, more quickly than you can than by digging up the literature yourself. And everything that I will say is in an old lecture notes of mine, where there is a whole chapter about essentially today's talk, And the references, the precise references, which I will just mention cursorily during my talk. So let's get started. Now, what is Bayes' theorem? Bayes' theorem starts with a complete metric space. Nobody knows what this will have to do with dynamics. It starts with a countable family of open and dense sets, a countable family, U sub k, and then you take the intersection. And Bayes' theorem asserts that if you are in a complete metric space, very general, then this intersection, of course, need not be open. Intersection of open sets need not be open, and just take the open intervals around 0 and intersect them. But the intersection is still dense in the whole space. And that means anything in the big space can be approximated by something in the set G. G is the A generic set, and for us, the elements of capital X will be vector fields, dynamical systems. And the properties of general dynamical systems are rather general and complicated and messy, and you cannot tell what is a bifurcation. A bifurcation in a vector field can be arbitrarily degenerate. And in our setting, the set G will be the good guys. G for good. They will show nice bifurcations, Hopf bifurcations, saddle node bifurcation, period doubling bifurcations, which you have heard about before. Okay, and this is the conceptual setting by which I start. And I will not speak about applications today. My last talk in the seminar series was about rather recent applications, how you find conditions for general metabolic networks to support the possibility of time periodic oscillations. And the result was like if you have a feedback loop of certain length, minimum length, or of certain feedback, some autocatalytic properties or so, when they are shorter, then the metabolic network can support time periodic oscillations and global Hopf bifurcation. But today, I want to give you the techniques on which this is based, and these techniques are old, even if the applications are very new. Now, the definition is that we talk about a generic set, or equivalent words are of second Bayer category. I never knew which is bigger. So second, 2 is bigger than 1. So there's first category, which is the complementary set, and second Bayer category, which are the generic sets, or residual sets. Residual is a problematic word. So I use the word generic. A set G tilde, any subset G tilde of X is called generic if it contains such a countable intersection of open dense sets. Okay, let me give you some examples about what happens generically. Generically, that is, well, in the sense just explained, generically, polynomials do not have multiple zeros. All zeros are simple. So simple zeros are much nicer, you know, polynomials, f of x. What does it mean, simple zero? F of x equals 0 implies f prime of x non-zero. This is a polynomial with simple zeros. So generically, there are no multiple zeros. What is the set X in this case? The set X is the set of coefficients of polynomials. Okay? The set of coefficients of polynomials. This is some r n plus 1 if I have a polynomial of degree n. That is our basic set. And the set of coefficients for which all zeros are simple contains a countable intersection of open dense sets. It is an open set here even, okay? Itself open. So it is, that set is open and dense. I will prove examples 1, 2, and 4 simultaneously with a single remark. So I will show you why this is true in a second. But more generally, generic maps from the reals to reals, high school maps, if they are once continuously differentiable, so now the space capital X is the space of once continuously differentiable functions, have only simple zeros. And moreover, now I'm getting closer, at least in notation, to bifurcation. If I have a map from a space Rn plus m, so I take m parameters, later m will be just one, a single dimension. If I have a map from Rn plus m to Rn, then the zero set will be generically for a generic set of such f, C1 again, of course, I forgot, C1, an embedded submanifold of dimension m. So the dimension is the dimension of the parameter space. And this is why in bifurcation theory with one parameter, we get curves of solutions. And if we have two parameters, we will talk about surfaces of solutions here, equilibrium solutions, f equals 0, okay? The zero set. No dynamics yet. And the reason for 1, 2, and 3, and 4 is just Sart's theorem. First of all, the F with such non-degeneracy will be an open set in a suitable Whitney topology. If you're worried about infinity, if you are interested in a compact set of X, then you can use standard C1 spaces. And Sart's theorem says that the set of regular values is residual. Okay, the set of regular values is dense, let's say, is dense. The set of regular values is dense. How do you do that? Well, this is Sart's theorem. I will not prove this for you. This is a subject of analysis, and often this is done by Lebesgue measure. That you say the set of regular values has full Lebesgue measure, and then the set of regular values is, of course, dense in the set of all values. So perturb, now only simple zeros, this is an open property. So we only have to perturb to get density. F of x or lambda x minus epsilon equals 0 if and only if f of x equals epsilon. And for this epsilon here, for this epsilon, pick regular value near 0. That's a dense set. So this is a perturbation which keeps polynomials to remain polynomials, and of course maps remain maps. And by this simple perturbation, a scalar in the first two examples and a vector in Rn in the last example, by this perturbation, you can achieve that a priori the zero set is a manifold of the appropriate dimension. So this is the rule of thumb that physicists have internalized when they say, well, n equations in m plus n unknowns have, I can eliminate the n from the n equations, n variables, and I end up with an n parameter set of solutions. Okay, so this has a foundation in genericity. Now, how does this help us with degree and degree theory and the like? So let me explain Brouwer degree next to you. And I assume no previous knowledge of degree theory, but a little bit of knowledge of bifurcation. Okay? So what is Brouwer degree? Brouwer degree tries to count the zeros. So task, count zeros x in omega of f from Rn to Rn. Now the problem is, if f looks like this, okay, y equals f of x, and if this is my f and I lift this f, I change this continuously to raise it, then the count may change. Two zeros may coalesce and become no zero at all. This is what we call saddle node bifurcation if the parameter lambda pushes this thing up. So if I consider f of x minus lambda. Now, the proper count, as Lautzen-Brauer in his famous dissertation thesis with David Hilbert in Göttingen around 1910, 1911, showed was that the proper count is the following. You count the number of zeros of f, and if you want to be a little bit pedantic, in a region omega, and you count the number of zeros, not the number of values, whatever other element of Rn you have here. You take any zero that you have. Now imagine this. You're told to count something that you don't know, and so you sum over the things which you don't know, but only theoretically, of course. And you take the signs of the functional determinants of the Jacobian determinant of the derivative, the signs. So you count a zero where the determinant of f prime is +1. You count this as a +1 0, and where this determinant is negative, you count it as a -1. And then you see here, you have a plus because the derivative is positive here. And here you have a minus, and +1 plus -1 is 0. So there is a zero count, and that zero count is homotopy invariant. This count is invariant under changes of f. That was the fundamental idea. Of course, Brauer did this differently in a topological way, but this is for generic f. For generic f. Because we already know that for generic f, 0 is a regular value. That means whenever f of x equals 0, f prime of x is non-degenerate, has maximal rank. So I forgot to say that. When I have a regular value here, i.e. f of x equals 0, implies rank f prime of x is maximal, in our case surjective. Okay, so this gave us this manifold here. And I forgot, generic n cross n matrices have only simple eigenvalues. This is also a nice one. I wish I had known this in linear algebra. To hell with all those Jordan blocks and off-diagonal elements and real and complex. Generic matrices, if you cough a little bit, have only simple zeros. That corresponds to the simple zeros of the characteristic polynomial, of course. Now, the Brauer degree for a regular value 0 can simply be calculated by the sum of the signs of determinants. So this is, however, not how you calculate it when you don't know the zeros. You calculate it by homotopy invariance. I will show you in a second how homotopy invariance works. In other words, if you change the f by a homotopy parameter, which in dynamical systems we call a bifurcation parameter, lambda. Topologists call it t, but for us t is time, and so we call the homotopy parameter lambda. Then this degree doesn't change, even though in between there may be degenerate zeros. How does this come about? Well, the idea is to talk about oriented paths of equilibria. So we have equilibria of x dot is f of lambda x. So now we are in a dynamic setting. And for generic f, we have one-dimensional curves now because the dimension of lambda is 1. Dimension of capital lambda. So think of capital lambda as the reals or an interval. And now I define E as the number of eigenvalues of the linearization with respect to x, which, because we are in dynamics, are strictly positive. So this is simply the unstable dimension of an equilibrium x at position lambda. Unstable dimension, E. And the Brouwer degree, unfortunately, because it is the sign of the determinant, counts the negative guys. It counts the, if you take -1 to E, then complex eigenvalues, of course, don't matter because they come in pairs. Okay, they come in pairs, so they do not change the even-odd parity. It is only important whether the unstable dimension here is even or odd. If it's even, -1 to the E is +1, and if it's odd, -1 to the E is -1. And the Brouwer degree, which I just introduced, because that counts the negative signs, the negative eigenvalues contributing to the determinant, is -1 to the total dimension times the number, the unstable dimension, which we prefer as dynamicists. Now, we already saw that we have generically paths of zeros in one parameter. So parameter is to the right, so we get bifurcation pictures. If we work a little harder, then we can show that the only possible degeneracy in terms of bifurcations is a generic saddle node, a quadratic saddle node. I will not prove that this holds generically here. I can give another talk on genericity, how you prove genericity of all these things I claim today, but that's, I will not do this today. Sorry, it's still a little bit early here. Now, in this path, I define an orientation. I define a direction. An orientation, a direction. I orient the path to the right if -1 to the E is +1. In other words, for even unstable dimension, I say follow the path to the right, to increasing lambda. However, if the unstable dimension is odd, even unstable dimension. However, if the unstable dimension is odd unstable dimension, then I orient the same path to the left. Fortunately, this definition is made so that at a saddle node, there is no conflict. You see, if I did this in a stupid way, not talking about even an odd unstable dimension, then perhaps I orient this path also to the right, and two paths go to the right and they are in conflict. They clash at the saddle node. But we want peace and harmony, and there is no clashes in our theory here. So we avoid clashes precisely by this even-odd definition, because as we follow this path, we know from bifurcation theory that a simple eigenvalue crosses through 0, and therefore the parity of the unstable dimension changes. So here's a simple eigenvalue crossing through 0. Unstable dimension, even, odd, and this allows us to orient all bifurcation pictures now. And I very much recommend when you look at bifurcation pictures that you think of this and think of the paths as actually walking along the paths as being given an orientation according to degree theory. The consequences are very strong of this very simple idea. One consequence is homotopy invariance of degree. What is homotopy invariance? Homotopy invariance means I take f of lambda x and I choose lambda as a homotopy parameter. Rather than a bifurcation parameter. So if you want to explain to a topologist what we are doing in bifurcation theory, then you say, oh, we are doing homotopies. And our homotopy parameter is called lambda instead of t. Now assume that I have such a family now of maps, one f for each parameter lambda. And in homotopy theory, the parameter space is always from 0 to 1. So I want to compare now the count with respect to a parameter of the zeros of my map. So here's f equals 0 in a region omega. And to count properly, I do not allow escape of zeros through the boundary of omega. No escape, okay? So no escape here on the boundary. And what is Brouwer telling us how to count zeros? He says, well, maybe this 0 here has a +1 as the sign of its determinant. Here's a +1 and here's a -1. That's the example I do. Now, the homotopy from here to there, I want to show that the Brouwer count of zeros does not change. That is extremely powerful to calculate because the meta theorem of topology and degree theory and the like is you never calculate the given problem. You always count for an easy problem which you know well, which you know better. And then you say the count is the same because Brouwer told you how to count with plus and minuses rather than just pluses. In complex analysis, the Brouwer degree of any zero happens to be +1. That's why in complex analysis, you have much better theorems on zeros than in real analysis. But that's a side remark. I will not go into that. So what's my count here? You see, I drew a complicated knotted link of curves here. So this may look rather complicated in say, three-dimensional space omega cross lambda already. But I just orient. I said +1 is oriented to the right. Great. +1 is oriented to the right. And -1 is oriented to the left. And this orientation is consistent here through the saddle node here, or there's a saddle node here, a saddle node here. But it doesn't matter how many saddle nodes I encounter, I still have curves. Now, suppose, so what arrives on the right? Well, on the right, a +1 is still oriented to the right. So this means out. This goes out. So plus means out on the right. And it means in on the left. But if I have a total count non-zero, then I have more going in than coming out. So something must come out on the right. So if you just calculate the plus and minus, these two cancel. And the total degree is invariant. Simply because whatever comes in on the left has to go out on the left, that is cancel, or come out unchanged on the right. This is homotopy invariance of degree. And now you have a way to define degree for non-generic f. Because if you have a non-generic f, you can approximate generically. But you can approximate in different ways. Now, approximate in different ways, but generically. So these are my different approximations. Do a homotopy between them with generic saddle nodes, and you see that the degree which results doesn't matter which approximation you take. It just doesn't matter. You always get the same degree by generic homotopy invariance. I should say that in his book series on functional analysis in volume 1, Eberhard Seidler used such an approach. Okay, we discussed a lot about that. As a corollary, let me prove the celebrated Rabinowitz global bifurcation theorem, which Jayan, of course, has used, and which says that if you have a bifurcation, for example, if you have a bifurcation point from a trivial equilibrium, f of lambda 0 equals 0, then that bifurcation generates an unbounded continuum or something which comes back to this primary line of trivial equilibrium. So this is a trivial equilibrium. Now note that this is not completely generic because I fix f of lambda 0 equals 0. And transcritical bifurcation is not generic. A generic perturbation of a transcritical bifurcation would resolve this bifurcation, for example, like this. Or it would resolve it like that. So that's what happens on a generic approximation. So we assume that outside that line, we have genericity. And in fact, we will prove a strengthening of Paul Rabinowitz's theorem. Namely, we look at any transcritical bifurcation from the trivial branch. So I look at a lambda star here. And I define a crossing number. I just check how many. So I assume a priori that these bifurcation points are isolated. So I do not allow a continuum here where eigenvalues linger around at 0 and change multiplicity and whatnot. So I take E of lambda plus goes from above to lambda star, and lambda minus goes from below to lambda star. So I count how many, what's the unstable dimension a little bit to the right and what is it on the left. And generically, this will be plus or minus 1. One eigenvalue goes through 0 left to right or right to left. And then I define the number z, a bifurcation index. You will see why I call this z in a second, which is minus 1 to the unstable dimension at bifurcation times chi. And if this is plus 1, I call it a source, and if it's minus 1, it's a sink. And if you chase the plus and minuses through, then here I have drawn an example with chi equals plus 1, E star even, so Z is plus 1. Then a source is simply the following. You have a degree along the trivial solution. So I can orient the trivial solution with path, just as I did before. And now if I perturb here to make this bifurcation generic, then I see that the bifurcating paths have to be oriented away from this source. So this is a source if Z equals plus 1, and towards a sink if it's minus 1. So at a source, the orientations along the trivial branch collide and give orientations away out of the trivial branch. And on the other side, they come in. Now, these branches are global. They have no further bifurcations. So the only thing that could happen is that, it can become unbounded in parameter space or in X. That's the Rabinowitz. Or it can terminate at another bifurcation point. But that other bifurcation point has to have a Z equals minus 1. Now, I'm sure Paul noticed that by the definition of the degree here of the bifurcation source and sinks, sources and sinks always alternate. So sources and sinks, not just in this example, but they always alternate. you just chase through the two cases where one eigenvalue becomes unstable and here another one becomes unstable. That would be a chi equals +1, but then the E changes parity. So if chi remains in parity, then E star changes parity. And if chi changes parity, that is, you go forward and you go backward with the same eigenvalue, then E star remains the same. So in either case, the z's alternate along the horizontal axis. So this is a refinement. And what do we do in the non-generic case? Non-generic. Well, approximate Fn to F. Well, if Fn of xn equals 0, then F of x infinity, if I take a limit, is 0. So the limit of these globally oriented paths becomes a continuum. And that completes the proof of the Rabinowitz theorem. My next example considers fixed point index. Now, fixed point index, we are, this is off. A fixed point index is simply the zeros of identity minus g. So g of x equals x if and only if f of x defined as x minus g of x equals 0. So since we have a way of a homotopy invariant way of counting zeros of f, excuse me, I have a homotopy invariant way of counting fixed points of G. Okay. And now we can see what is the local generic fixed point index. The fixed point index is simply the degree. So I is simply the degree of identity minus G. And if we want to calculate that, it is plus or minus 1. And it is simply minus 1 to the sigma plus, where sigma plus now counts the spectrum. And I should say the counts are with algebraic multiplicity, of course. Counts the spectrum of G prime, which is, so here's the spectrum. Here's the real part of the spectrum. So there's minus 1. There's plus 1. And sigma plus counts the spectrum bigger than 1. The real parts don't really matter, only the reals count. Because if we have complex eigenvalues here of G prime, they come in pairs. They do not affect the parity. So complex doesn't matter. Only real eigenvalues matter. So it is sufficient to count the eigenvalues over here which are real and bigger than 1. So this is the real interval. A little remark, which will be important later on, is that the fixed point index of the second iterate can be different from the fixed point index of the first iterate. You see, if g of x equals 0, then g of g of x equals 0. Any fixed point is a fixed point of the second iterate and higher iterates. But the second iterate, has the square. So for the second iterate, I have to study the spec g prime of x squared, right? That's the derivative of the second iterate. It's g prime of g of x, which is x, times g prime of x. So this time we count in terms of the original eigenvalues, we also count the guys sigma minus on the left. Now, if you continue to the third iterate, then the minus guys become minus again. So the fixed point indices of the iterates simply alternate generically. They alternate between -1 to the sigma plus and -1 to the sum. So it's ping pong, ping pong, ping pong, ping pong. Now we know all the fixed point indices of all iterates, if you are interested. So this is a special structure which we cannot, this iteration is something which doesn't make sense for zeros. You do not iterate the vector field at 0. You let it run, of course, but you cannot iterate. It doesn't make sense to study x dot is f of x. Now, as a corollary, we can prove very easily that any map from Bn to Bn, any continuous map, possesses a fixed point. That's Brouwer's fixed point theorem. That's Brouwer's celebrated fixed point theorem. Brouwer. I will not do this line by line now because time is already a little bit advanced and I have a lot of fascinating stories to tell you about periodic orbits. But let me just mention the basic idea. The basic idea is that you say the degree is invariant under the homotopy x minus lambda g. If you take lambda equals 1, you're looking at fixed points of G. But if you take lambda equals 0, you are looking at the degree of the identity map. And the degree of the identity map, it's a linear map. Where are the zeros of the identity map? They are at 0 in the center of the ball. And therefore, the degree is non-zero. And therefore, for lambda equals 1, you have a fixed point. Yeah. Now, a most fascinating topic, in my opinion, is what degree theory tells you at a period doubling bifurcation. So here I have drawn a period doubling bifurcation for you in lambda cross x, and a point here is a periodic orbit. And of course, we pass to the Poincaré map. And in the Poincaré map, we say, okay, we have a fixed point, fixed point, but here we have an eigenvalue, a Floquet multiplier, -1 at period doubling. And we have a crossing. So we are already warned that to count fixed points appropriately in a Poincaré map, everything is in Poincaré map. To count fixed points, we should watch sigma plus, the Floquet multiplier is bigger than 1, and sigma minus, the Floquet multiplier is less than -1, real ones. And what happens at this bifurcation is if I take sigma plus, sigma minus here, so this defines my number sigma plus, sigma minus. The sigma plus minus on the right of the bifurcation are same sigma plus, and sigma minus may be sigma minus +1 or sigma minus -1, depending on whether we cross out of the unit circle or into the unit circle. So I have drawn one of these two examples here. However, at the doubled branch, we get the unstable dimension of the real multipliers of the square, the eigenvalues of the square of the linearization. So we get sigma plus sigma minus as, so this refers to 1 infinity, and this refers to -infinity, -1. And now I have written a 0 here. Well, it could be that they are purely imaginary Floquet multipliers, which under the square become precisely negative. But they come in pairs. So generically, they will be a little bit off the imaginary axis. And in the square, they will not appear on the negative real axis. So that's why I can omit those. That's why I write a 0 here. Now, Kathy Elligood came up together with her then advisor, Jim York, with a terrible example of a so-called Jacques handle. So this is, you have to turn this by 90 degrees. Then it is like you are holding a beer mug, okay? So you have this jug handle and you drink the beer. So this is the handle where you put the hand, okay? Can such a bifurcation happen? Not in 3 dimensions due to linking properties. You see the secondary orbit would be linked to the first, and they cannot unlink at a saddle node bifurcation because the second orbit winds around the first one twice, over here and once over here. But from 4 dimensions on, such a bifurcation diagram can happen. And now let me remind you what people in global bifurcation theory did before. People in global bifurcations theory said, oh, bifurcation of periodic orbits is nothing but bifurcation with 2 parameters. Namely, we can rescale time in x so that our periodic orbit becomes a periodic orbit of period 1, not necessarily minimal period, that's a big problem, and p appears as an explicit parameter. Now, when you do that, then you just have an ordinary bifurcation problem with 2 parameters. And this is what J. Alexander and Jim York used. J. Alexander used homotopy of spheres, Sn plus 1 to Sn. It's a non-trivial homotopy group here, and discovered by Heinz Hopf, not Eberhard Hopf, the guy with Hopf bifurcation, but the topologist. And they showed global Hopf bifurcation occurred from ordinary Hopf bifurcations, just in analogy to the Rabinowitz theorem. A very nice result in space P, lambda, and x. So P, the period, became an implicit, continuously varying parameter in that theory. And later, Massabo and Vignoli did S1 equivariant degree, and Jorge Ise, and so on. Jorge Ise had very new results on global Hopf bifurcation by this method at the same conference where I presented the results of my dissertation thesis before I got the thesis. So I was extremely nervous that somebody else had obtained my results, and we discussed for a long time. And now I can tell you the main difference. So what happens to Kathy Elligood's jug handle example in that theory? Theory is nice, but always look at examples. Examples, examples, examples. A theory is no better than the best example it has, okay? So what does this simple jug handle beer hall example, Kampai example, what does this tell you? Well, in space lambda x and period, which I have to keep track of now, I have the primary branch, I have a saddle node over here, and period increases, 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 and comes back to the same bifurcation, but from the secondary branch. There is no bifurcation here because the period is wrong. The period of the period double branch is, of course, near 2p. So I end up at a copy. So this is primary, and this is copy 1. Or primary 1 and copy 2, okay? I end up at something which looks like another branch in their theory. But really, it's the same orbit. Just saying, oh yeah, but I have period P. I also have period 2P. I have any multiple of myself as a period. So any object appears an infinite number of times here. And when I start from 2p, I say, okay, who cares? So let me follow this branch, let me follow this branch, let me follow this branch. Whoops! But I have started with 2p. Now I end up at 4p. I omitted the 3p in there to avoid clutter. And if I go from 4p, I end up at 8p. And so on to p tending to infinity. Well, to the np, I should say, not p. This continuum of Cathy, this beer handle, this jug handle, is not a global object. This is perfectly in a compact region of phase space, and the minimal period remains bounded. But in the Alexander-York theory and their topological adepts, this is global. Global, not global. So in my opinion, Cathy's example, which dates from 1981, killed a lot of the developments, most of the development that these people pursued through the 90s. For 20 years, they were going on with these examples, and it was, they didn't look at the examples. Sorry for them. Now, instead, John Maleparé, I think it was his idea, suggested a different index. He said, well, actually, what we have here on the left of the bifurcation is, or for any periodic orbit, is a sequence of indices for the Poincaré map, for the second iterate, for the third iterate, ping pong, ping pong, ping pong. We already saw that this is all ruled by sigma plus and sigma minus. And now let us look at this example, what happens here. We have sigma plus, we have sigma minus here, we have sigma minus plus 1 or minus 1, and then by homotopy, 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 all near minimal period, we end up with a 0. Now this can only happen if the flow K multipliers in the example, which were sitting on the negative axis, one of them became less than -1, so we have a sigma minus plus 1. But then, so one marches out here at period doubling, but then they all have to evaporate. They all have to become conjugate complex and go elsewhere, actually reappear at the positive axis once the turn of the beer mug is completed, of the jug handle. This means that this number must be even. Otherwise, one of them would remain. They cannot escape here. They cannot escape to infinity. So in other words, sigma minus must be odd. And this led them to define an orbit index as the average of the fixed point index I of the first iterate and of the second iterate. Just the average. They averaged over this periodic index sequence. And if you calculate that, the first index is -1 to the sigma plus. The second one is -1 to the sigma plus sigma minus. Then you get -1 to the sigma plus times a half, 1 plus -1 to the sigma minus, which is 0 if sigma minus is odd, and which is -1 to the sigma plus, so the index of the first iterate, if sigma minus is even. What does it mean that sigma minus is odd? It means that the unstable manifold of the periodic orbit is non-orientable. This is why this is called a Möbius orbit. Sigma minus even means that the unstable manifold is orientable. Is non-orientable. And this is orientable. And then they said, let us define a snake. Let us define a snake as let us give an orientation to paths of periodic orbit and orient them to the right if this orbit index is +1 and to the left if it's -1, just as we did for Brauer degree. What does this do in this example? Well, because sigma minus is odd here, this is Möbius. So here phi equals 0. And phi equals 0, they say delete. Do not follow Möbius orbits. It's a little bit anti-German, but okay. So let's not follow the German guy. If you encounter a non-orientable, unstable manifold, do not follow such a path of orbit. Just delete from your bifurcation picture. Now here, this will be orientable. So it has an orientation, maybe this one. I don't know, it depends on the sign of, on the parity of sigma plus. And here on the saddle node, we get the continuation of this. So we get a circle. So in this case, Aligood jug handles are isolas. Now, towards the end of the talk, I have to speed up a little bit as usual. Let me tell you what a snake is. Now, snake was the contribution by Jim York. He always had wonderful, wonderful words. And this is not edible snakes, but this is snakes for continuation of periodic orbits. Ignore phi equals 0, I said, delete. And for the remaining ones, pick an orientation to the right in parameter if phi is +1 and to the left if it's -1, just as we did with degree theory. But this is a degree for orbits which come in circles. We just draw a single point, okay? But this reparameterization by orbits is here. This is a degree for periodic orbits, not for points on periodic orbits. And what happens at a saddle node? At a saddle node, we just orient through. What happens at a period doubling? Well, if we ever arrive at one, not from an isola hovering somewhere, then we continue along the secondary branch. The secondary branch is never Möbius because the secondary branch always has sigma minus equals 0. Okay, and this guy will be deleted if we come from the left. So we can never run into cycles. Never. This is a global generic continuum, and we only have to figure out what happens at Hopf bifurcation, analogously to the transcritical bifurcation. And by exchange of stability, let me cut this a little bit short. There is an index with Shui-Ni Chao called Zhong. Shui-Ni Chao, who recently passed away, he called it, so he introduced a Chinese symbol for a bifurcation index. Zhong, center. This is something, fortunately, I don't have to explain in your country. I had to explain a lot when I was doing this kind of theory. Some gave me the nickname Django instead of Django, you know, the Western movie hero. So they gave me the nickname of Django because with this Zhong index, I did bifurcation theory. If you take -1 to the unstable dimension at bifurcation times a half the crossing number that we had before, because now pairs of imaginary eigenvalues cross the axis, then this will be a +1 for a source and -1 for a sink. And the relation simply is by local exchange of stability. You see that at bifurcation, sigma minus is always 0 or even, because the Floquet multipliers are exponentials of eigenvalues. Sigma minus must be even. And I get an orientation away from a source and towards a sink. However, now the jongs along a trivial solution need not alternate. You may have another +1, and you may have another +1. And this is what happens if eigenvalues cross from left to right. Then the crossing number is the same, and E changes by an even number each time. So E doesn't, -1 to the E does not change at all. So if you have several pairs of eigenvalues crossing to the right after each other, the branches cannot just return, like in the Rabinowitz example, because all these are sources. And therefore, if the sum of jongs along a certain reference bifurcation set are non-zero, then you get global Hopf bifurcations of snakes generically. The additional option is unbounded minimal period. The difference to the Alexander-York theory is that period need not and should not be required to change continuously, but it can jump by factors of 2. And the proof is simply the consistent orientation of snakes at Hopf, saddle node, and period doubling. So that proves a global Hopf bifurcation theorem, and that is the theorem I used in my talk for metabolic networks. I can either stop here or give you a few remarks on how you do the approximation of general vector fields by generic ones, because not all vector fields are generic. And my advisor, Villiega, was very, very opposed to genericity because he said, but you never know whether a given model is generic. And of course, he was right. And he was very suspicious of my applications because I liked mathematics at the time much more than applications. But there is a notion of virtual period which allows you to go from the beautiful generic world of snakes and jongs to the non-generic situation by approximation. And the main result here is that the limit of minimal periods may not be a minimal period of the limit, but it is a virtual period of the limit, where virtual periods just are minimal periods of pairs x, y, where x is the periodic solution and y solves the variational, the linearized equation. So the trace of approximation, so to speak, trace not in the mathematical sense, but the indication of generic approximation is in the linearization. And mostly, you will not have periodic solutions, non-trivial periodic solutions other than x dot of the linearization. And so minimal period and virtual period coincides. But sometimes you can have periodic solutions here. And in the case of Hopf bifurcation, where x is stationary, the limiting, the y, the virtual period, is a periodic solution of the linearized equation, which is the purely imaginary eigenvalues. Thank you very much for your attention at this stage. And if you want to know about virtual periods, I'm happy to explain. Thank you very much.
Thank you very much for this very brief but also very detailed introduction and history about the global index theorem. And I think this theory is kind of new to everybody, but you are welcome to ask questions and give remarks.
I'm sorry, it is so old that it becomes new again.
Yeah, truly. So questions. Maybe let me begin, okay? So I don't understand why you eliminated the Möbius case. It's just for a convenient choice. I mean, you can choose another. I mean, you can eliminate the non-Möbius case, or there's a reason.
Okay, so here I eliminated the Möbius case
Yes.
to avoid the following problem. In the Alexander York setting, this can come from some Hopf bifurcation.
Yes.
And then I follow my path, and J. Alexander would say, yeah, but it's global and it's continuous. But I'm saying, yeah, but you must be kidding. You call such an object global? This is not global. This is an artifact. This shows your complete inability to control minimal period.
I see.
And if you look at this from a more general, like, equivariant perspective, because this has the big advantage of being an S1 equivariant bifurcation problem, and that's why they got all excited. They wanted to do equivariant degree theory, equivariant topology, what have you. Then in equivariant topology, the same problem arises. You have a symmetry action, and the big advantage is here you're only calculating zeros of a map in Banach space, but there's compactness and so on and so forth. Okay, so this looks much easier than that at the expense of a single parameter. And Jay said, but I am the topologist, I know homotopy theory, and of course you can do 2 parameters and 3 parameters and do stable homotopy groups of spheres and so on. So there are reasons why they got all excited about this. Okay, so then they had multi-parameter bifurcation results, and this was generalized. They never solved this problem. And the main problem on the equivariant bifurcation theory side was to control isotropy.
Yes.
If you have a solution of some PDE, and the solution is, let's say, in 1 dimension, okay? And the solution is asymmetric. It's not odd or even, but the limit could be odd or even. So the limit of zeros can have more symmetry than the approximating zeros. Here, under this shift, the limit of such objects will have period 1. But who guarantees you it doesn't have period 1/2 or 1/3? So you do not keep track of minimal period. And there is a rescaling. So in this setting, any solution P lambda x of t, you understand this is meant to indicate the orbit, also solves. Now let me see. NP lambda x of nt or t over n? NT. For any solution, I always mess it up. This also solves. So that you have a rescaling symmetry. So this manifests itself as a parameter symmetry. And general S1 equivariant problems do not have that parameter symmetry. Of course not. And they never address that point.
Mhm.
But this index, which is, of course, handmade, so to speak, it is not, you know, topology is a Mercedes. Sorry, no advertising. Porsche, oh, those are all German. Lamborghini, okay? So you sit and you rush through the landscape and everything is a priori, categorically homotopy invariant, what have you, all the big words. Does it solve the actual problem? Does it address the peculiarities which arise from dynamics? And it does not. And that's why we have to get out of the Lamborghini and walk on foot with machete, you know, through the jungle. And that's what the thing on the left does. And that's why I took sides. And that's why later in my habilitation thesis, I proceeded to combine the symmetry breaking aspect and the virtual periodicity aspect. And nowadays I see virtual period as a corollary to virtual symmetry, to something that comes from a completely different sort of Golubitsky philosophy. Okay.
Okay, I see. Thank you.
You're very welcome.
Yeah. So, questions, other comments?
This is a very nice talk.
Thank you very much.
Thank you very much. So, Professor Fiedler, is it possible that if you can deliver your lecture notes to the interested audience?
Yes, I can, sure. I can send you PDFs of the annotated, and I will delete this, sorry. Of the annotated, so to speak, the blood splattered manuscript and the original manuscripts. This is what I always provide when I do classes, with pleasure. Okay, pleasure.
Oh, thank you very much. That would be very helpful. Yeah,
You're very welcome. And also there's the reference here. Lecture Notes Math 1309, 1988, where you have, so that is about symmetry breaking, which you should not read. But if you want to give this, but if you want to give this to a student for a survey or so, there is a section there on the non-generic theory, on the non-equivariant, the non-equivariant theory. Okay, no symmetry. And that is better than the dissertation. At dissertation, I did not know how to write. And Willi Jäger was trying very hard to convince me to write a good dissertation. But I thought he just did not understand and what I was telling and so on. And I wrote a bad dissertation. The result is not bad, but the style of presenting is pretty awful. Okay. And later I tried to do amends. He was very, very patient with me. So.
Thank you very much.
You're very welcome, really.